Okay, welcome to the next part of this topic. We'll pick right up where we last left off. So the last time we finished a number of examples, and then we got to this example, which looks remarkably complex here. And it actually is. It's actually, I guess no pun intended, it's a complex vector loop is required to solve it. So it's going to take two vector loops. That's an example of one of those. So all right, so let's look at this mechanism. And by the way, just to give you a warning, this mechanism is going to be what you'll become intimately familiar with your project. You're going to be designing the links and location where the links join so that as this moves, bar 6 stays as straight as possible. And that's not trivial. It'll use a lot of the theory I'm going to teach you in this course, but you'll need to be very familiar with this. If you notice, this aspect of the link is the Chevy-Chev mechanism from, so links 1, 2, 3, and 4 from the first topic. So go back and look at that and see how that moves to see how this point up here moves in a straight line. And then this guy is designed, this link 5 is designed to hold 6 as straight as possible as link 2 moves. So, but anyway, with that, I'm going to show you how to analyze this, do position analysis, because it's a great example. Again, if you want your own experience, go ahead and put me on pause and try and do it. But if you don't, I'm going to give you the answer here now, or at least one answer. Now, bear in mind, there's again, like I said, there's multiple answers to these, but this is one possible answer. So we could do a vector and by the way, this should be fairly easy just because there's a bunch of pin joints, and it's pretty easy to know you connect the pin joints. So this one obviously describes R2, that captures the rotation and magnitude of link 2, and then this is R3, R4, and R1. And again, the arrows are drawn arbitrarily according to our convention. And that's just one vector loop, and that will capture the Chevy-Chev mechanism. And we're just kind of ignoring 5 and 6 for now, but that's one closed vector loop. So, if we just start at a random place and walk either clockwise or counterclockwise, it doesn't matter. As long as we stick to the convention going from tail to head, it's positive, 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 negative. And so you can see that up there, that's the positive, 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 negative for those signs. Okay, and we can solve this, before we put it in component form and solve it, let's just make sure the vector loop we drew for this is good. So we go through using our bookkeeping approach, and we say, is the magnitude of R2 something we know? Is it something we can measure? Is it something that changes as the input changes? And yes, it is. It does not change, but yes, we do know it, so we put a check above it. It doesn't change. It stays fixed as theta 2 changes. Is the angle of R2 known? Well, sure, it's the input, so you put an I there. Okay, what about the magnitude of R3? Yes, we can measure it. It doesn't change. That length doesn't change as theta 2 changes, so we put a check there. And the angle is unknown, so it's question mark. Remember, according to our convention, since there's the tail, we draw a dotted line, and then the angle would go around that way. Okay, so that's theta 3. Okay, R4, again, we know the magnitude, so there's a nice check there, but we don't know the angle, okay, and that's one thing we know. It would be from horizontal here all the way around there, okay, and then R1, we know the magnitude, and we do know the angle, okay, because this is ground, it's not moving, it's not going to change with respect to theta 2, and right now the angle is just 0, all right, okay, so that means we've drawn a good vector loop. It's two equations in the component form with two unknowns, two question marks. Okay, so we can solve that. Okay, but what about the rest of the mechanism? Well, we need a whole other vector loop to solve the full thing. We've only solved part of it. Okay, and so that's why this is called a complex vector loop, because you need multiple vector loops. Okay. Okay, so to draw the vector loop here, remember, and this is one. There's many solutions, but let's just say I drew a vector connecting 1 to this point. Okay, and that's a point on link 6, and this is going from 1, so I did R16, or I could have said R61, or I could have said anything, except I can't call it R1, R2, R3, R4, R5, or R6. Okay, so it can be anything, just not one of those, because it doesn't capture any of the links by itself. It's just a useful vector. Okay, and then we're going to draw one from there to there. Now this is a point on 6, and that's a point on 6. Okay, so that's well named R6. You need to call that R6. And then here's R5. And remember, these are links that weren't captured by the first vector loop. Okay, and then we draw this one. This one goes from 5 to 1. So we did 1, 5 or 5, 1, or we call it whatever we want. This is obviously related to R4, but since it didn't span the whole thing, we've already named one R4. We have to give it a new name. Okay. Okay, and then of course we connect this, just use R1 again. So we want to make sure when we draw any vector loop, we close it, that it's one full loop, so that when you add everything together, they can equal 0. That's the whole point of the vector loop equation. Okay, and so this is a second necessary vector loop. All right, so again, we'll start in location, let's say here, and we're just going to walk clockwise. Okay, according to the, just how we arbitrarily drew the arrows. We follow our convention, and this would be plus, 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 minus. Okay, and then we're going to go through and see what we know. Okay, so R16, this vector, do we know its magnitude? And does it change as theta 2 moves? Well, we don't know it, and it does change. So you'd think, well, it could be a question mark, and so is the angle. Its angle would be from here to there, right? And you'd think, well, that's something we don't know. So you'd think 2 question marks. But we're going to put 2 C's because they're actually constrained to stuff we already know from the first vector loop. So for instance, we know that R16 equals basically R2 plus R26, which is I drew it as a green vector that points from that point to that point on 3. And I called it 2, 6 because it went from 2 to 6. A point on 6 or 3, it doesn't matter. And then R62, it could have been called just anything that's not taken, you could call it. But obviously, this one is related to R3. Okay, and so hopefully you agree with me that R2 plus R26, as I've defined it, is R16. Okay, and there's basically 2 equations in here that can solve for and account for the 2 unknowns here. Okay. And just know that, if we go through and ask ourselves, do we know the magnitude of R2? Yes, we do, and we actually already solved it up there. Do we know the angle of R2? Yes, we do. It's the input. Okay, do we know the magnitude of R26? Well, sure, we could measure this. That doesn't change from that pin to that pin as theta 2 changes. And do we know its angle? Well, it's the exact same as R3. See, R26 angle is the same as R3. And remember, we've solved this vector loop already, so we now know the 2 question marks. So that those question marks are no longer question marks because we had 2 equations, we had 2 unknowns, just pretend we solved it because it can be solved. Okay, so we know that that's the same angle, so therefore we know everything in here. Now, a little trick, if I had defined R3 going this way, and I had defined this vector going this way, then it would be a little different because R3's would be 0. It would be the angle of R3, it would be theta 3 plus pi, right? But because they're both pointing this way, then they're both right. Then they're both from the horizontal all the way to there. So they're both equal in this case. So just make sure, even though they have a very related constrained angle, make sure the arrows are going the same way. But if they're going opposite ways, just plus pi, right? Okay, but in this case, they're equal. So we now know everything in here. We have 2 equations, 2 unknowns. So we do know this because we've solved all this and it's constrained. Okay, and then R6, do we know the magnitude of R6? Yes, we can measure that. It doesn't change as theta 2 changes. So we know that. Do we know its angle? No, we don't. Okay, and this is the one that's going to vary. And for your project, you're going to want to try and get it to vary as little as possible. Now, some students for their projects, they force that angle to be 0, and that's not a good idea because oftentimes it's impossible for the mechanism to always be 0. And so what you want to do is allow it to vary, treat it like a unknown, which it is, and just try and minimize how much it fluctuates, okay? So this is definitely an unknown, and that's actually what we most care about. We want to keep that not rotating as much as possible over the full range. Okay, R5. We do know the magnitude. We could measure that. It doesn't change as a function of theta 2. And its angle, we don't know. Okay, we'd have to draw a horizontal there and go all the way around there. That's going to change. Okay, it's another unknown. Okay, R15, we do know its magnitude. Again, we could measure the distance between these pins and it doesn't change as theta 2 changes. And its angle, we also know, okay, it's actually constrained by virtue of the fact that the angle of R15 is the same as R4. Remember, R4 pointed from here to there, and because these are going the exact same direction, when we draw from the horizontal all the way around, it's the exact same angle, so they're equal. So we could say it's constrained through this equation that we already solved. Remember, that was a question mark there, but we've now solved it. We know it, so it's the same thing. And remember, if we had drawn the angle this way, we would have had to say it's that angle, plus pi, right? So because they'd be going in opposite directions. Okay. Okay. So, okay, very good. So now again, we know this, the magnitude. We know its angle is 0 as it's drawn here. So. Now, from these two vector loop equations, we had the two equations, two unknowns, we solved for those. And then from what we solved from that, we had a number of constraint functions that we introduced in here that we can now solve. And we have, again, the two equations here with the two unknowns, so we can solve for everything. So that because we have enough equations as there are question marks, and we have enough things to define the whole thing, you can know your vector loop is good and will work, or your vector loops, so to say, and then you can solve everything, okay? And you'll need to do that for your project. And again, what you care about for your project is plotting this angle as a function of theta 2. As theta 2 changes the input, if you put a motor on here, as theta 2 changes, you're going to want to be able to solve how does theta 6 change, and you're going to want to design all your lengths and where you put the pins so that theta 6 varies as little as possible. Okay, but again, don't force it to be 0 because there's many ways it can't be forced to be 0. Okay. Okay, so all right, so we've talked. So that's a huge topic on vector loops. Like I said, it's the most important one probably in the course. There's nothing too tricky about it, but you got to wrap your mind around being able to see simplified vector loops and get experience drawing them and knowing when they'll be solvable, okay? But once you have them, the question is, how do you solve them, okay? Because sometimes if they're not linear equations and you have two equations and two unknowns or more, right, then it can be pretty complex solving it. So I'm going to now present an analytical approach, a numerical method, and then displacement of a point method, okay? And anyway, you'll see the analytical solution method is brute force. I wouldn't necessarily recommend it on an exam because it can take some time unless it's a super, super simple problem to solve. Otherwise, it can be pretty tedious. But once you solve it, it's the most powerful. It's a closed form equation, direct way to find your solution. Okay, so we're going to do an example for how to do it. Say you have a slider crank mechanism here. Remember, when we're doing position analysis, we draw the vector loop. We did this before on the right here, and then we marched around it using our convention. We came with the vector loop equation. We found we have two equations in there and two unknowns. We simplified the two equations in the component form, and we identified, okay, we know R2, R3, and we know R2 and R3, and right, and we're given theta 2, but the unknowns we want to solve for is theta 3 and R4. Okay, so we have two equations and two unknowns where the unknown is theta 3 and R4, which is how much that slider slides and how much that link R3 rotates. Okay, and so we want to solve this. Basically, the goal is to find theta 3 as a function of theta 2, give me the answer. R4 as a function of theta 2, give me the answer. Okay. And this can be kind of tricky because, like I said, it's not linear. So I'll teach you some tricks how to solve these if it's not linear, and things that are commonly work for mechanisms, because you'll notice most mechanism vector loop equations are made of cosine and sine, just for the different components x and y, and there's ways to deal with cosine and sine to simplify them. So one approach you can do, okay, is rearrange this vector loop equation above, where you put R3 equals R2 minus R4 minus R1. So you just rearrange that. Another way to think of it is you could just add this to that side and set that as equal. So now it's all the, this part's on that side of the equation and everything's over there, okay? And then what you can do is, you want to get rid of theta 3 so you can solve for R4. So the way to get rid of theta 3 is take this equation and dot product it with itself. So if you take R3, the vector R3 up there, and you dot it with itself, remember when you dot product things, you take the magnitude times itself, okay, and then you times by cosine the angle between them. But if it's itself, then cosine of 0 is going to be 1. So that will get rid of theta 3. Okay, so if we write it a different way, take R3 and dot it with itself, okay, then what you're going to get is, so we took this equation, and we dotted this side with itself, and we dot this with itself, and you can see here's R3 dotted with itself, and that ends up equaling just R3 squared, right? The magnitude, the length of that R3 squared. Notice cosine 3 went away. That's the whole trick, to get rid of cosine 3. And then we dot this with itself, and we can distribute this, dot that with that, dot that with that, then dot that with that, dot that with that, dot that with that, and just keep distributing, and you'll see you get all this. And right off the bat, as you look at this, you can see R1 dot R4 is 0, right? R1 dot R4 is 0 because they're 90 degrees, or pi over 2 radians. And anytime you dot product orthogonal vectors, they go to 0 because cosine of 90 is 0, okay? So let's simplify these. Again, these two are dotting themselves, so this one goes to R2 squared. These are dotting themselves, it goes to R4 squared. These are dotting themselves, it goes to R1 squared. And then you can see that these go to 2, R1, R2. Cosine the angle between them is theta 2 plus pi over 2. And then this one is 2R2, R4. Cosine this angle between R4 and R2, okay? Okay, so now notice there's no theta 3 in this because we did that dot product trick. And so now we just have to solve for R4 as a function of theta 2. And that's really what we want, right? And so the way to do this is to recognize, put it into this quadratic formula form, and recognize that R4 is the what we're interested in. And so we've got an R4 square, R4, and 0 there. And we know that A is 1, B is there, C is all this by lumping this together. And then we can use, again, the quadratic formula here. Negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. Plug those values in, and you will get this. Okay, so this is the solution of R4 as a function of the input theta 2. And you'll notice everything in here is something we know or is the input theta 2, right? And so we've solved that, but now we have to solve theta 3 as a function of theta 2. And to do that, you notice theta 3's in this term. So if you kick both of those on this side and then you divide this equation by that equation, well, now you can get rid of the R3 there and turn it into tangent theta 3. And you get this plus this divided by this plus or minus that. So you can see there's that. Okay? And then, if you do the arctan or tan inverse here, then you have your answer. Notice this is tan inverse of everything we know, R2, R1, R4, which we solved here as a function of theta 2, and then here's theta 2 in there. So now we have theta 3 as a function of theta 2. Okay, so we've solved it. So that's the brute force analytical way to solve this and get closed form equations. And if you can do that for a mechanism and you're willing to do the brute force of solving it by hand, then you've got your solution. And this is the completion of position analysis where, you plug in any theta 2 and we give you any theta 3 and R4. And now you can know the position of every link as a function of the input. Okay? Now, there's something a little strange about this. You might have noticed there's a plus and minus in there, right? So it looks like there's two solutions. There's one solution where this is plus, and one solution where this is minus, and that would cause this to have two solutions as well. So it turns out for every theta 2 you plug in, there are two different configurations that would geometrically satisfy that configuration. And you could imagine, so R2 cosine theta 2 is the length between this pin and that pin on the x component, and this value here is the length from there to there. So you could imagine when the solution is plus, you'll find an R4 and a theta 3 that is this configuration you see there, but when its solution is negative, and that affects this one, you'll see this configuration, which is kind of as if you rotated theta 2 a little bit this way and then walked around to the back and saw it from that configuration. So it would still work with all the vectors and all the geometry. That would be a viable mathematical solution for the same theta 2. Okay, so that's principle number 1. Is whenever you solve a planar two-dimensional mechanism, with 2 equations and 2 unknowns, you're going to pretty much always have 2 different solutions for any one input that correspond to 2 different configurations that could mathematically work. And you need to be smart and vet them to know which one you're talking about. If you're plotting a plot of, say it started in this configuration, you want to plot theta 2 starting at 0 all the way to 2 pi, and you want to see how R4 changes and you're plotting that, you want to make sure you're always using the solution that corresponds to the right configuration so you don't get any discontinuous jumps and suddenly the mechanism warps to some other spot, right? So you need to, like for instance, you'd always want to use the plus for both of these if you're doing that for this configuration. And the other configuration, you'd always want to use negative, okay? But that's kind of obvious for the analytical solution here. Okay, so then there is a slightly easier mechanism I found than that. That's much easier to calculate all that brute force that I've given on a past exam that you'll see. But most of the time, even that, you'll notice that whole approach that we used and using that trick of dot producting R3 to get rid of the theta 3, it's pretty brutal, and you wouldn't want to do that on an exam that's timed or anything. So. And you'll see very quickly it gets even more complicated. This is a 4-bar. Remember, we drew the vector loop. We did this. We did all the check marks and saw we could prove it. Here's the component form. If you recall, we've already done this in previous parts in this topic. And we know everything in these equations. The 2 unknowns is theta 3 and theta 4. So for a given theta 2, what's theta 3, theta 4? That's the question there. And you could solve it, and you could use that same trick. You could dot product, R3 with R3 to get rid of theta 3, and then solve for theta 4, and dot product these to solve for theta 3, vice versa. But it's pretty intense. And I say on the slide here, we'll do it on the board, take notes. But since we're just doing a video recording here, I've posted those notes with the other lecture notes. So. Make sure you go through that and check the math and see how brutal it is to just solve, even for a 4-bar, a closed form analytical equation to find theta 4 as a function of theta 2 and theta 3 as a function of theta 2. But once you have those, you have the most powerful closed form equation, and you can fully describe a 4-bar. And then these things just get even more brutal and vicious as the mechanisms get more intense and complicated. So if you want the final solution to be, like I said, closed form, most efficient for computational purposes, then you'd want to do this if you have the time and you're able. But there's a much easier way to solve this in a general way that's numerical, and that's what I'm going to teach you now. So this was the by hand analytical approach. Now we're going to do a numerical approach called the Newton-Raphson approach. And this approach, you can take any mechanism and it will numerically solve it. You can just write a MATLAB code and it'll solve it for you in an iterative numerical way. Okay, but there are some tricks to it. So, but I'll definitely want you to code this in MATLAB and get it working and get comfortable with it, because you'll definitely need it for your project. Okay. Okay. So getting back to a 4-bar, let's see how we would use Newton-Raphson to solve the 4-bar example. Okay. So again, you get to your component form after drawing your vector loop and finding it solvable, and you have your 2 equations and your 2 unknowns, and you want to solve those for when these equal 0, and then it corresponds to the 4-bar, and you'll get what you want. So here's the trick I want you to think about. So if you just instead of setting these to 0, say you set these to functions of 2 independent variables, okay, that are actually the outputs that you care about. So say this is just a function. Say R2 and theta 2, which is the inputs, because you do know it. You know R3 and R4, And this is just now, you're going to call it a function of theta 3 and theta 4. Same thing here. This is a second function, and it's a function of theta 3 and theta 4. Okay? Now, those functions, we got two functions with two variables in each function, so multivariable functions, and they really don't make any practical sense until they equal 0. When these two guys equal 0, then it solves the vector loop for 4-bar mechanism. Okay? And for any mechanism, remember, once we draw the component form, they always equal 0. So you can make any of the two equations functions of the two output variables that you care about solving. And if you can solve these two functions for when they equal 0, or it's also called their roots, then you can find the theta 3 and theta 4 that satisfy this the vector loop equation for any known theta 2. Okay, so it's kind of a weird way to think about it. Okay, all right, so we could solve that, but let's, so I'm just saying here we're going to use the Newton-Raphson method to find when these two functions, what values of theta 3 and theta 4, cause those to be 0. Okay? And a much easier way to teach Newton-Raphson is to do kind of a one-dimensional equation. This is two equations with two unknowns. We're going to do one equation with one unknown and use Newton-Raphson to teach it that way, and then I'll show you how to do it with the two-dimensional equations, basically, with two inputs. Okay, so say you had up here this just single function where x is the input variable, and you've just got one input variable, and that's that. Okay, and if you plot x versus f of x, then you get this red squiggly line here. Say we're interested in finding what's called the root of that equation, which is when f of x equals 0. We want to find what x value makes f of x 0. In other words, when that red squiggly line crosses the x-axis. That's when f of x will be 0. And you want to find the x's where it does, so these 3 gray dots. And notice there's 3 of them because it's x to the 3rd power, right? So whatever the highest power of that polynomial equation is, that tells you how many roots there will be, how many times it'll cross the x-axis, okay? Now you could just analytically solve this by hand and find the roots, but that can get very tricky, especially when you have two-dimensional equations, right? Solving the roots of these equations to find when the 4-bar works, or is the case of the 4-bar, is tricky. Okay, so I'm going to teach you a different way to do it. Okay, and the key is the Taylor series expansion. Okay, you might recall from the first slides of topic 2, I taught math that you would need, and I taught you about Taylor series expansion. Before I lecture on this, if you don't remember, please go back and review that relationship, what a Taylor series expansion is. Okay, because you really need to understand that. But basically, the idea says if you have some function, you can approximate that function, or actually dead-on equal that function, if you take an expansion and you add all infinite components, okay? Where the first thing is just that function with some random number plugged in, then the derivative of that function with the same random number plugged in, times x minus that random number, plus, if you recall, 1 over 2 factorial times the second derivative, all this same stuff, times this raised to the 2nd power, plus 1 over 3 factorial, third derivative raised to the 3rd power, and it just keeps going on forever. And if you add all the components forever, they literally will equal this function, whatever the function is. Okay, but it approximates it as you start cutting off higher order terms. And what we're going to do to find the roots of this function, or really any one-dimensional function, is we're going to take its Taylor series expansion, we're going to cut off all the higher order terms after the linear ones. So that, from 1 and 0, the first two, the 0th one, the 1, and we're going to cut off all the second derivative and third derivative and all the stuff above there. Okay? And so this is going to be a very rough approximation. It's going to be barely approximating it, but it's a good start, and we're going to do an iteration from this. Okay? So we can say this is sort of approximate after we cut off all the higher order terms to this function. Okay? And Okay, so note we got rid of the higher order terms. And so now we're going to reorganize this, because remember, we want to solve for x that makes this guy equal to 0. That's when the roots are 0. Or those are the roots that make it 0. Right? So let's force this to be 0 and solve for x for some given